My name is Advik,
And I'm Sonia.
and we are undergraduate freshmen at USC. And today we'll be presenting our work on wildfire spread prediction using deep learning. So, firstly, why focus on this topic, right? So, being from California, we all know that wildfires are a huge threat, especially in Northern California. Firstly, they're very costly. They've cost about $50 billion in terms of damages, and they're destructive and they cause heavy pollution. So when we were doing our background research into the topic, we found that most of the wildfire prediction models focus on where the fires originate from, not where they actually spread to. And what we want to do is we want to try to figure out where they spread to because of a couple of reasons. Firstly, it can help improve fire response. And secondly, it can help with resource allocation for the emergency crew. And what we try to do with this model is we try to utilize more modes of data so we get an accurate representation of where these fires might spread to. So how do we go about this? So there's a data set published by IEEE on next day wildfire spread. So this has about 18,454 events, which is basically snapshots of wildfires at day N, which consists of basically 12 events, which include elevation, wind direction, wind speed, etc. So in our model, what we try to do is we try to take a 12-channel input that includes all of these features and output a one-channel output, which is basically a fire mask at day n+1. And this fire mask is basically a probability distribution of where fires could be at day n+1.
So for the model, we chose to use a UNet architecture, and on the slide it says pre-trained, but actually we trained it from scratch since we weren't able to find any pre-trained models that were trained on data similar to ours. And then, yeah, as mentioned earlier, we put all of the 12 inputs into one 12-channel input, and we also normalized it by mean and standard deviation, and then outputted a fire mask with the probability of fire per pixel. And then we applied a threshold to classify it as fire and no fire. So in terms of the results, we looked at the accuracy and recall since the classes were so imbalanced in terms of fire and no fire, and they both converged around 0.75. And when we actually look at what our model predicted, you can see with the ground truth and the predicted model, for some of them, it actually did match pretty closely. But for a lot of them, like on the bottom, you can see that it pretty much didn't match at all. So this leads us to how do we improve the model? So we think that a huge part of the problem is because of the imbalance between the classes. So also, when we were looking through our data set, we did notice that there were a few events where the fire mask didn't actually contain any fire. So we're thinking of filtering that out and also cropping some of the fire masks so that the classes are more balanced. And then we're also thinking of using a different loss function. Right now, we're using the weighted cross entropy loss function, but we're looking into using one based on like overlap of area rather than the numbers. And in the future, we want to sort of visualize which features are actually important. So we want to use GradCam to create saliency maps of every channel in the input, see like what the model is actually looking at, and this will also help us debug the model. And then this will also give us information on which modes of data are actually important so we can optimize, and yeah. So that's all. Thank you for having us, and we're happy to take any feedback and suggestions.